And wonderful. Okay, cool. I don't know if off on. Okay, well, that's working. I can do it this way. Maybe. Yeah. Oh, there we go. Okay. Okay, we're in good shape. All right, so this is, I'll take my study team first. This is our core team. And I think Tanya Halliday was one of the speakers last year at your seminar series. So I've been working pretty closely with her, which has been really exciting. And then this is mainly our graduate students. And as it turns out, this was, let's see, not February. This was the very end of April. It was almost May 1st last year. And it has been snowing today in the mountains at Salt Lake City. So for those of you who go there to ski, which I know at least a couple folks do, hopefully we're setting up another good year. Cool. So I'll go through this quickly. So I want to give a little bit of background about sleep duration and risk of diabetes, and then I really want to provide some information and data on why I think the timing of sleep is important. I'll go over some of my real world sleep extension studies, and I want to highlight my new studies. And then I have a feeling I won't have time to talk about peripheral circadian rhythms, which is why I put a question mark on it. And I'll do some summary conclusions. So for sleep duration and risk of type 2 diabetes, there's really a lot of epidemiological data out there. This is a meta-analysis. I think it was published back in 2010 in Diabetes Care. And so this was mainly prospective trials, but it was showing that people who have, I mean, you can see here, a lot of these are short sleep, which is less than 5 hours typically, compared to a reference, which is like a little bit more than 8 or 7 to 8 hour time range. So the overall analysis here was a relative risk of 1.28. And most of these meta-analyses that have been done fall in that range, like around 1.3, increased relative risk for developing type 2 diabetes for people who report short sleep duration. So we know that this data exists. This is another meta-analysis. It was from Evan Potter's group, and they were trying to look at the relative risk compared to a lot of traditional risk factors, so like overweight, family history of diabetes. You can see they had physically inactive lifestyle down at the bottom there. And then they wanted to compare that, or try to compare it to some of the sleep risk factors that people think are important. And so you can see the highest relative risk was for obstructive sleep apnea, difficulty maintaining sleep, sleep duration less than 5 hours, and sleep duration less than 6 hours. It's not on this figure, but it falls right below that. So, they're just trying to put this into perspective, that they think, these relative risks, at least for sleep-related factors, are in the same range as a lot of the traditional risk factors that we think about. And so it might be important to consider sleep in this story. This is a summary of work from a handful of laboratory controlled trials. So it's kind of going the opposite direction now. And it's showing the percent impairment in insulin sensitivity. Most of these were measured by intravenous glucose tolerance tests. I don't think clamps are on here, but we've done some clamp studies. And so all of these studies are essentially taking perfectly healthy young adults who normally sleep 8 hours. They don't have elevated BMI. They don't have any psychological disorder. They literally don't have anything wrong that you can detect with them. And when you restrict their sleep for, this is like 4 to 8 days in the lab, down to like 4-hour sleep opportunities, maybe 5-hour sleep opportunities. So this is pretty extreme sleep restriction. We see these impairments in insulin sensitivity, which it's in line with that prior data, and it supports that perhaps this impairment in insulin sensitivity is one of the factors that could be driving those associations that exist. And this data is relatively consistent across a whole bunch of different labs. So it is pretty clear that this happens when you take people who get, I really want to stress it, they get 8 hours of sleep normally, and you restrict them down to 4. Okay. So I want to talk about why, that's kind of the story about like why people started caring about sleep and risk of type 2 diabetes. And so I want to sort of introduce you to circadian physiology. This might be totally review for some folks, but I want to kind of put it into perspective. And so for our human clinical trials, the way we quantify the timing of the circadian clock is to look at a 24-hour profile of melatonin. And so this is what a typical melatonin profile might look like. So it's generally low during the day, and it goes up at night, and it comes down during the day. And under circadian aligned conditions, people would be sleeping for 8 hours while melatonin is high. And so we typically, if you have this full profile, you can quantify a threshold. And when it's above, when melatonin goes above that threshold, we'd call that the biological night. And when it's below it, that's the biological day. And so the phase markers that we typically use are dim light melatonin onset, which is the up triangle, and then dim light melatonin offset. So when it comes down below that threshold is the down triangle. And then again, like that's the biological night based on the timing of the central circadian clock. And so that's, I'm just highlighting it there. So that's what we consider the timing of the biological night. Now, if you get short sleep duration, you could get it many different ways. This would be an example of going to bed later, but waking up at the same time. And because in the real world, most people are going to get light exposure when they're staying up, unless they're staying up in complete darkness, they're going to get light exposure. And so light exposure here, when you're getting short sleep, by staying up later, that light exposure is going to shift your clock. It's going to delay it. And it can delay it by up to 2 to 4 hours, depending on how bright that light exposure is and sort of when it is in your personal circadian rhythm. But that's what a delay looks like. So it's going to shift everything later. And it's what that means now, if you're waking up, you can see there's this big interval between when you wake up and the end of your biological night. And so we've termed that morning circadian misalignment. And so I'll show you actual data. This is just like theoretical right now. And then to complete the picture here, if you go to bed at sort of the same time, but wake up really early, you're going to get light exposure in the morning. And the timing of that light exposure is going to shift your clock in the totally other direction. So that's going to be in advance. Everything's going to be earlier. And so that's going to make you, you're going to start to feel sleepy earlier. So if you maintain that, you might sort of shift your bedtime earlier. But nonetheless, it's going to shift it in the other direction. So that's why it's like really important. Like we don't say like just wear blue blocking glasses 24 hours a day, because the timing of when you get exposed to light is really important. And so that's kind of like theoretical data. This is a prior study. It's a little bit older now. It's published in 2015, but I think it's important. It highlights this point in a laboratory trial. And so I want to highlight the eligibility criteria. This is true for most of the laboratory studies we've done. So we confirm that our participants have no medical, psychiatric, or sleep problems. And we do that with a physical exam, blood chemistry, psychiatric evaluations, and a sleep disorder screen, either in the lab or at the sleep clinic. We confirm they're drug-free, non-smokers, low to moderate habitual caffeine users, habitual sleep of 7 to 9.25 hours per night. So that's self-reported. And then we confirm that with a actigraphy. And then they're not allowed to work shift work in the year prior. And for 3 weeks before enrolling in the study, they can't travel outside of the mountain time zone. And then because we've done these studies at the University of Colorado and now at the University of Utah, we require that they were at high altitude or 1,600 meters altitude about for a year prior to being in the study to try and eliminate any like major adaptation things to living at high altitude that could impact our data. So when we say like the healthiest people we find, this is who they are. And the idea for these studies is not really to like necessarily translate these data to people who are getting short sleep in the real world, but to sort of understand the human physiology of what's going on when we manipulate sleep. And so this one was a crossover protocol, 8 participants in condition order A and then 8 in B, which I'll show you. They came into the lab and had 3 days of baseline. We administered an OGTT on day 2. I'm not showing you the data, but we also did intravenous glucose tolerance tests on 2 days after each of these OGTTs. So we do have IV GTT data. I'm just not showing it to you. Day 3 of baseline, they were in dim light. So I didn't mention it, but we have to keep participants in dim light. So to get that true, like accurate melatonin profile, we need to keep participants in dim light, which is about 5 lux. And so 1 lux is 1 candle about 1 meter away from your eyes. And so we keep them in dim light because light acutely suppresses melatonin. So to get an accurate measure of that melatonin profile and not have light like acutely altering it, we have to keep them in dim light. So they're in dim light on day 3. Then we did a controlled condition where they had free access to food. So this was energy balanced food intake. And then for the rest of it, they had free access to food. It was still 9 hours time in bed with the OGTT and then measured the melatonin again. And then they went to a 5-hour sleep condition where we kept the midpoint of sleep centered. And then they have the OGTT and the melatonin. And then for condition order B, it was 8 participants again. It was the same thing. They just did condition insufficient sleep or sleep restriction first, followed by the control. And so this is what happened with the Matsuda index calculated from the OGTT. And you can see that that was reduced during the insufficient sleep condition relative to the control and the baseline condition. This is as expected compared to all those other studies that I already shared with you. So this is very consistent with those data. We saw a similar magnitude of change with the intravenous glucose tolerance test. So this is their melatonin timing. So if I go back to this, it's really important. Like during the sleep restriction, like they were in normal room lighting this whole time, except for when we were doing the melatonin. So they got that light exposure during the sleep restriction. So at baseline, that's the start of their melatonin or dim light melatonin onset. The black box is their sleep opportunity, and then melatonin offset is the down arrow. This is the 9-hour control condition. So that's when they had free access to food. So they were overeating during that condition a little bit. But this would suggest that overeating like they were is not going to impact your central clock, which it didn't. You can see no major changes there. And then this is the 5-hour insufficient sleep condition. So even though we kept the midpoint of sleep centered across all these, there was a delay in their melatonin onset. And so you can see that relative to baseline. And there was no change actually in their melatonin offset. But again, there's this really big phase angle. And that's really, so like circadian data gets a little bit confusing because it's like circular. So you always have to talk about like phase angles, like this time versus that time. But so this is a wider phase angle there. And so we termed that morning circadian misalignment. So now they're getting up in the morning, they're potentially eating breakfast, trying to function. And for several hours, it's still their like circadian biological night. And so we thought perhaps that would be a contributing factor with the impairments in insulin sensitivity. And so in this study, we did an association. And so the worse that morning circadian misalignment was, or the larger the magnitude of that was associated with the impairments in insulin sensitivity. And so you can see like the insufficient sleep dots, they're the open squares. Those are typically clustering down in that kind of region of the graph. And so that was really interesting. It kind of like, that was the first study that showed like there might be this association between the circadian misalignment during short sleep duration and impaired insulin sensitivity. This was replicated in adolescents with PCOS and a couple other studies. So I also just want to highlight, we did a weekend recovery study, which was very similar. We did 5 days. Actually, I guess I have the protocol. I'll just explain it. So it was 3 days of baseline, the same as the prior study. And then this was a randomized controlled trial, and there's other groups, but I just want to make that clear. Like there were other groups in this study. I'm just highlighting the weekend recovery group quickly. And so you can see they did 5 days sort of simulating a work week of insufficient sleep. And then on this Friday into the weekend, they could sleep whenever they wanted, as much as they wanted. But on Monday morning here, they had to get up early again, which is really that there. And so they could self-select their time on their bedtime on the weekend or on Sunday night, knowing they had to get up early. And they self-selected a time on average that got them 6 hours of sleep. So they were kind of self-selecting short sleep duration in the lab there. But nonetheless, we measured on these days prior to the clamp. So these CCC days, it's not indicated. They were in a whole room calorimeter, but we also had them in dim light. So those are the days we measured melatonin timing. And so I really want to focus on day 11 here, which is that Monday immediately following the weekend. So that's the baseline. It looks similar to the baseline in the prior study. That's work week 1, which is those 5 days. And you can start to see this shift happening again where it's delaying. The weekend, that's their timing of sleep on the weekend. We didn't measure melatonin, so there's not triangles. And then this is that Monday morning following the weekend. So there was actually a significant delay in both the onset and the offset of melatonin there. And so again, is what we see is this sort of delayed sleep timing. You can see they really slept in really late over the weekend. Certainly that's not doing anything but potentially contributing to more circadian misalignment. And so if we think this circadian misalignment part of the sleep restriction is what's driving part of this, getting a weekend of recovery sleep where you stay up late and sleep in really late might be actually worse for you than trying to get sleep during your normal time. So that irregular sleep cycle is kind of we'll just say wreaking havoc on your circadian timing. And that was the same thing there. So this was a study we just got published. I think it's just, maybe it's beyond impressed, but we just got it published recently, like the past month. And so what we did is we went back and looked at, in all of the studies that we had run in Colorado over the past like 15 years, we went back and looked at all of the baseline conditions. And so this is, again, all healthy participants. There were about 65 participants. And we just quantified during the baseline segment where sleep was adequate, where was people's dim light melatonin offset falling relative to their wake time. And so this dashed line is their wake time, so that's 0. And you can see like the distribution here is that the majority of participants in sort of the real world with electrical lighting have a dim light melatonin offset that's occurring like 1 to 2 hours after their habitual wake time, which would suggest that this sort of level of morning circadian misalignment is somewhat prevalent even among these healthy participants without restricting their sleep. This is data that was published some time ago, but it's worth highlighting. It's a camping study. And so what we did is we took participants, they did 1 week in the electrical lighting environment. We basically said, just do whatever you normally do. We're going to measure your sleep with an ActiWatch. You're going to come into the lab. We'll measure your melatonin, which you can see there. And then we're going to take you camping in Colorado for a week, and you're going to be exposed to nothing but campfires and sunlight. And so we're going to remove all electrical lighting, and we're going to see what happens to your melatonin timing. And we did that during the summer solstice and during the winter solstice. So I'm showing you data from the summer solstice. So this is in the electrical lighting environment, and this is consistent with, kind of what we're seeing here. You can see this is the end of their average sleep, and you can see melatonin offset is occurring after that. So there's a little bit of that misalignment there. And in the exact same people, after a week of camping, you can see this is during the summer solstice, so like short daylight. You can see there's actually a little bit of a compression from sort of the start to the end of their biological night, but we see a big shift here. So from that point to that point, that's shifted significantly earlier. And this misalignment is now gone, and they're actually waking up after the end of their biological night, which means we didn't assess their alertness, but you would predict that they are waking up more alert, less groggy, feeling better, and like ready to tackle the day. We decided not to actually analyze their sleep specifically, other than their sleep timing, because it was a bit fragmented. Like we were camping in tents, so like it was definitely more fragmented sleep during camping versus living at home. But we did see, if we remove all electrical lighting, we do see that shift. So that was really cool data. Let's see, when we published the winter camping one, I think it actually got picked up by Saturday Night Live. So it's like the peak of our work there, being on Saturday Night Live. Okay, just so you have it, this is the first one. So this study is this one here that we just got published. And then this is the first camping study. And we have another camping study that's also published. So, to kind of bring it all back, I'm not going to show you data from this. It's not a super robust study, but in this one, it's the group from Harvard, and they tried to do sleep restriction in the lab in dim light conditions. So they did comparable sleep restriction to what we did. They just had participants in dim light the entire time. So that eliminated that circadian misalignment completely. And they did meal tolerance tests, and they didn't see any impairment in sort of that glucose response on that meal tolerance test. So that's also consistent with this, that sort of irregular sleep or that misalignment is potentially driving these changes that we see. I'm going to totally shift gears for 2 seconds for those of you interested in lipid metabolism. I am working with someone, Scott Summers, who maybe some of you know, at the University of Utah, who's done a lot of work with ceramide metabolism. And he basically said, are ceramides changing at all in any of these sleep restriction studies? So we measured ceramides with Scott, and I don't want to go into it too far, but Scott's overarching hypothesis of his whole career is that ceramides are a toxic lipid that are contributing to cardiometabolic disease risk, and they kind of block insulin signaling. And some other things too. So that's just kind of a schematic from one of his review articles. And so we did go back and measure ceramides in some of these studies. And as it turns out, this was during 5 days of sleep restriction. So the red dash line is baseline, and then what you're seeing is relative to baseline. So we did see an increase in some of these ceramides during the sleep restriction. And then this is during, I termed it sleep extension for our grant, but it was 5 days of recovery sleep. And we did see those ceramides, some of them come back down a little bit, which is the direction that's, it's consistent with like the changes in insulin sensitivity that we're seeing. These changes, I'm not showing it, but these changes here were associated with the changes in insulin sensitivity in that study. I will say a couple of things, how this might actually be happening. I can't say for sure. We haven't really dug into this any further, but we are following up on it. Scott has also, there was a lot of overeating happening in these studies, and Scott has recently just done some acute, like really big overfeeding studies and measured the ceramide response. And he's seeing that even acutely overeating is kind of driving changes in ceramides, like an increase in ceramides. And so I can't, there's no way in these data I can disentangle, like, is it like because they're sedentary in the lab? Is it because of the sleep specifically? Is it because they're overeating in the lab? But it's an intriguing finding that, we'll follow up on and see if it is meaningful. So I want to talk a little bit about real world sleep extension studies. So kind of as I started transitioning to Utah, I was trying to think about like sort of next step and moving beyond these sleep restriction studies in the lab. And so for my K, I got money to do a 4-week sleep extension study. And so I'm going to talk about that here. There's some intriguing findings. We have about 3 to 4 more subjects we need to run in that, and then hopefully we can get it published soon. And so kind of the goal of this was, first of all, like if we recruit people with short sleep duration, so people who are getting less than 7 hours of sleep per night, can we get them to sleep more in the real world environments? Like that was kind of question 1. And then, so that was sleep duration. And then we're also looking at insulin sensitivity with an oral glucose tolerance test, circadian timing. So we do have them live in the lab for a couple of nights. And then as kind of some exploratory secondary analyses, we're looking at free living energy expenditure by doubly labeled water. I don't have that data yet, but we should have it literally like within a week or 2. Then we are tracking physical activity with the ActivePal device. And then throughout some parts of the study, we're looking at the timing of food intake with picture food diaries. And so for eligibility criteria, it wasn't, we're kind of initially going like, if we just go one step beyond what we're doing in the lab and still recruit healthy young participants to try to like understand like physiologically what might be going on. That was kind of our rationale for picking this population. But as it turned, like I think it's maybe a more unique population than I initially sort of expected. And so these are essentially healthy young adults who are getting short sleep duration. And so we may have inadvertently found people who are functioning just fine on 5 to 6 hours of sleep per night. So we can talk about that a little bit more. But so we do blood chemistries, a clinical sleep disorder screening. So we know they're sleeping overnight at our sleep clinic. So we know they don't have apnea or anything like that. They don't have insomnia. They're drug-free, non-smokers, low to moderate habitual caffeine users, very similar to before. Their reported habitual sleep is less than 6.5 hours per night. And we do confirm this with wrist actigraphy because about 20% of the people, they actually sleep like 7 to 8 hours or even more with wrist actigraphy, even though they're reporting not getting this amount of sleep. Let's see, they're not allowed to do shift work. They're not allowed to travel more than outside of the time zone. And Salt Lake City is a little bit lower than Denver, so it's 4,000 feet altitude. So this is the protocol. It's my K, so it's kind of a pilot study. So it's a single arm trial. So we have 2 weeks of baseline monitoring. So that's days 1 to 13 in the free living environment. They come into the lab and we have them in dim light conditions to capture we're trying to get dim light melatonin onset and offset, but we don't have quite the full 24-hour profile. And they're doing the OGTT and we're doing other blood draws there. And then they do 4 weeks of sleep extension. We're trying to get them to increase their time in bed by 2 hours per night. And so these are healthy young adults. They don't have sleep disorders. And so like, at least hypothetically, they should be able to sleep more if they spend more time in bed. And I'll show you the data. We are getting them to sleep more. And then they come back to the lab at the end of the study to repeat all those assessments. The doubly labeled water, we're getting that for the first 2 weeks during baseline, and then the final 2 weeks of the intervention. I said we use the ActivePal. Okay. So this is the change in sleep duration. This is the data we've analyzed so far. We actually have more participants who have completed, but so this is the individual subject data. So we do have one person who actually got less sleep during sleep extension, one person who had virtually no change. And then everyone else has increased their sleep duration. This is the average sleep duration during those 4 weeks of the sleep extension, which also like it starts to beg the question like, what is the appropriate time frame to be capturing sleep? Like, should we be averaging it over 4 weeks? How should we be doing that? And this is the average increase. So it's about 0.75, almost zero point 0.8 hours on average of an increase in sleep duration. So this is by no means like as extreme as the sleep restriction we were doing in the lab, but we're pretty happy actually with what we're getting for sleep extension here. Like we're definitely getting a change in sleep duration. This is the week by week data, which is it's kind of interesting. You can see this; these are the folks at baseline, and there's not, I didn't totally really know what to expect. We haven't done this before, going like week by week. The one thing that we see, I mean, it's not tapering off, which is good. We're kind of concerned if like maybe that would taper off over time. We do see like these sort of error bars on the box plots are actually getting a little bit tighter. So, I think that's a good sign. I don't obviously know like long term how long this would be. It's a pretty intensive intervention. I mean, we're like assigning them bedtimes. They report every morning when they went to bed, when they woke up. We get that electronically. So like literally we see what they're doing every day. And if they start to fall off the intervention, we reach out to them after 2 days. So, I mean, it's pretty intensive and like hands-on as far as the intervention is concerned. That I was just highlighting the 7 hours time in bed there just to show that like, yes, we are increasing their sleep duration, but like all participants are not on average always above 7 hours, which is the sort of magical recommended length. This is the sleep efficiency. So we're actually measuring this with the Dream headband, which it's a headband that has dry EEG electrodes in sort of the front and the back of it. So it's kind of like an ambulatory PSG system. It's not super widely used in research, but I do know a lot of folks who have been using it. And so I think it's probably a little bit more accurate way of assessing sleep efficiency in the free living environment compared to the ActiWatches. And is what we see here is no change in sleep efficiency. And, minus those kind of 2 lower outliers, everyone's around like the 90 to 95% range, which for young, healthy adults, we would expect to be them in that range for sleep efficiency. So that's what we like to see. And the other concern is like if you just ask people to spend more time in bed and they're not able to actually sleep more, their sleep efficiency is just going to drop off. And this could actually start to induce like, if they start to develop anxiety around that, like not being able to sleep in bed, that could actually start to push them towards like insomnia. So, we are aware of that and want to be careful about it. And so we're glad we're not seeing that drop off in sleep efficiency. As far as sleep timing goes, we're seeing that most people are achieving this by going to bed earlier. So this is across the weeks of the study. So baseline, and then this is week 3, 4, 5, 6 of the study, which is the 4 weeks of the intervention. This is the individual sort of bedtimes. And you can see that people are gradually sort of drifting towards a little bit earlier bedtimes. And that's typically how most of them are achieving the sleep extension. This is the change by participant from baseline to the average during sleep extension. So you can see directionally, most of these arrows are going in the direction that would be earlier. So they are getting an earlier bedtime. Is how they typically seem to be doing it now, as opposed to waking up later. This is the eating window. This is from the 2nd week of baseline and the final week of the intervention. And, we were kind of interested in the lab when we restrict people's sleep and give them free access to food. We find that they eat more food and they tend to eat more food late at night when we're restricting their sleep. There's a lot of food available to them. It might just be helping them stay awake, et cetera. And so we were just kind of curious, like, is that even what's happening sort of at baseline? Like, what do we see with their timing of their food intake? And then is that changing during sleep extension? These are not statistically different right now. And I think like if you look at NHANES data, I think about the average sleep duration, timing of food intake is about 12 hours. So basically from first calorie to last calorie. If you look at, for those of you who are familiar with the literature, like Sachin Panda's group has done a lot of stuff on time-restricted eating interventions. They quantify the timing, like their eating window, as an eating window across like a week or 2 weeks that captures 95% of the calories consumed. And so if they eat on a couple of days, like they eat really late, but on a couple other days, they eat really early, like that could increase that 95% window and really expand that eating window duration. So in some of Sachin's data, I mean, he's reporting like 14 or 16-hour eating windows. And so I guess my point is here, we're not seeing like these really long eating windows. They're just taking a picture of all the food they're eating. And so, we're seeing kind of around the range that other folks are reporting and no major differences. So it doesn't look like that might be like changing dramatically in these people. This is just an example of one person's physical activity data from the ActivePal device. And so each ring going out is a different day of the study. And I highlighted that this is one person who had like a very consistent sleep schedule and shifted their bedtime earlier throughout the intervention. So this is baseline. And so the red is estimated moderate to vigorous physical activity. So you can see what that is. And I highlighted the times here. So that's 11 p.m., 10 p.m., 9 p.m. So you can see during baseline, this person was going to bed around 10 p.m. and sometimes staying up a little bit later. If you look at it carefully, actually, never mind. It is when you can see the weekends here when they're like sleeping in really late. But this is what happened during sleep extension. You can see they consistently started going to bed before 9 p.m. And they did a really good job with that. So I just kind of wanted to show that like we're interested in how maybe these types of sleep interventions might be interacting or starting to change behaviors with physical activity and the timing of physical activity. This particular person, that's their step counts. I mean, this is one person. We haven't looked at this for the whole group. I'm just saying like we'll have step counts. In this particular example, directionally, they decreased steps during sleep extension. But I don't want to imply that that means anything more than that's one person's data. So after going through all of that, this is kind of the most intriguing data. It is statistically significant. I just haven't put it on the stats on there, but the p-value when we last assessed it was 0.02. And so this is Matsuda index from the oral glucose tolerance test. And right now, as it turns out, it's significantly decreased during sleep extension compared to. And that was part of going through all of that other data to show you like what could be contributing to this impairment in insulin sensitivity. Granted, it's a pilot study. There's not a control group. So we maybe don't want to put too much stock in it, but it is a really intriguing finding because I obviously hypothesized that we would see an improvement in this. And certainly not a decrease. And so this is the individual participant data. And I just wanted to this is rather consistent across participants. So this is baseline, and then the red is sleep extension. And I ordered this from the people who are decreasing the most to increasing the most. And you can see most of the participants at this point are showing somewhat of a decrease. And we just have a couple of participants who have shown an improvement. So here's my best guess. I mean, we don't know what's going on with the circadian rhythm data yet because we haven't analyzed that, but it's getting analyzed very soon. So I'll be very curious if it's not necessarily like by going to bed earlier, I wouldn't anticipate that that's changing their circadian clock in a direction that's contributing to this, but we need the data to know. So it's an intriguing finding. The other kind of aspect that we haven't analyzed yet is the sort of sleep regularity. And so this is work from Andrew Phillips, who's now, he's someplace in Australia. He developed what's called the Sleep Regularity Index. And I just kind of want to point out what this is. It's an index based off of actigraphy data that takes, at least a week of data, but a week or any more. And it calculates this index, and it's a scale from 0 to 100, with 100 being like perfectly regular and 1 or 0 being perfectly irregular, meaning it's pretty obvious like what you can see here. But the point is you can have adequate sleep or insufficient sleep, and that can be regular or irregular. So you can see these folks, like this is an example of someone who has really irregular sleep, but they're averaging over 8 hours. This is someone else who has also irregular sleep, but they're averaging under 6.5 hours. And you can see what their sleep looks like by those black bars. Like it's clearly very sporadic. And basically this index is just, it looks like at each epoch of the actigraphy data, and it says like, are you asleep on like how many days out of the entire data set are you asleep at this epoch? And it does that epoch by epoch. And so if you're always awake and always asleep at the exact same epochs, that would give you 100, so perfect regularity. And then you can see the same example on the right here, where there's someone who has over 8 hours of sleep and under 7 hours of sleep, who is very regular with their sleep. I'm not going to go into it in detail, but there's data that exists now that shows it's association data, but it shows that regardless of sleep duration, people with more irregular sleep have a higher risk of type 2 diabetes. And I don't want to go into it, but it's well, I guess I'll say it really quickly. If you look at model 2 for both of these, the sleep duration variability, and then they did also sleep onset timing variability. Both of these, so that's the relative risk. It's 1.97, 2.10. That's after accounting for sleep duration. So it's about a twofold increased risk of type 2 diabetes for people who have really irregular sleep schedules after accounting statistically for sleep duration. So that data would suggest that perhaps the regularity of sleep is a really important factor to be considering. And then literally like 2 weeks ago, there was data published in a really big data set that showed that it looked at all-cause mortality and looked at sleep duration and the sleep regularity index. And the associations were much stronger with the sleep regularity index. So there's this data that's emerging that might suggest that the sleep regularity is important. So we'll calculate that in our study. We can look at it in a couple different ways. And it's hard to say. I don't know at this point, but maybe by increasing their sleep duration, somehow it's actually become much more irregular, and maybe that's a contributing factor to the impaired insulin sensitivity. Just looking at my time. Okay, so for my R01 that we just got funded, we're kind of expanding on this. And I want to just go through it really quickly, just kind of explain what we're doing. Also, I'm probably accepting one more graduate student to start in the fall, and then maybe the following year, a postdoc. So also, like if you're a graduate student here and you're really interested in this and maybe want to do a postdoc, let me know, because we have money for it. So this is in people who we're moving to a little bit higher risk population. It's older adults than we were studying. It's up to age 49. And they have overweight or obesity. So it's a slightly higher risk population than what I was doing. So we do 1 week of baseline ambulatory monitoring, overnight assessments for a clamp, and I think I put it there. Yeah, so they'll be in dim light to get their circadian rhythms. We're doing fasting blood samples and then a clamp to assess insulin sensitivity. And then we're doing an 8-week sleep extension intervention with a healthy lifestyle control group, randomized 1-to-1 with a sleep extension. And then they'll be repeating the same laboratory measurements. And so kind of our key outcomes on this is the change in sleep duration, the potential change in insulin sensitivity, and then we're also the main outcome for the fasting blood samples is ceramides. And we'll see, we might try to add some tissue biopsies to get at some things a little more precisely. And then this is a pilot study that we have going on. And I just wanted to highlight it because I think it's interesting in light of like sort of what we're seeing with our sleep extension data and sort of the idea that the circadian misalignment might be as or more important than sleep duration itself. And so this one, we're recruiting people with short sleep duration and overweight or obesity. And we're doing a circadian intervention. So it's actually a very similar protocol to the R01. And so it's 1 week ambulatory monitoring, the overnight assessments in the lab, measure their melatonin, doing a fasting blood sample, the OGTT. And then we have the intervention, and basically this intervention, following it, it's going to be the same measures. This intervention it's really simple, but so we'll see what happens. We're just giving them light boxes for really bright light exposure for 1 hour in the morning to try and like shift their clocks the correct direction, which would be in advance. So that would reduce, like if that shifts their clock, that would reduce that morning circadian misalignment. We're trying to reduce their food intake so they don't eat late at night. And then, so not reduce their overall intake, but just reduce that late night food intake. And then we're having them wear blue blocker glasses that are really, really dark. They're not like the blue blocker glasses you get off of Amazon. These are like way more intense than those. And by the way, we ordered like 50 of those to test them. And a lot of them don't really work at all. We tested them with a photometer that like gives you the color spectrum. And we tested it with like different lights and like how much blue light they're blocking. They don't really work, just in case you think they do work. if you get more expensive ones, they do, but you can get them. I mean, you can get a pack of like 10 for $10 on Amazon. So you get what you pay for, maybe is the lesson. Um, but nonetheless, so we're doing this circadian intervention and we're tracking their sleep as well. And so, the idea is to really see if we do the circadian intervention, does it sort of realign their circadian rhythm with how we would expect it? And if so, what happens with insulin sensitivity, what happens with their sleep, et cetera. And so I want to leave time for questions. So I think I'll probably skip over this, but I'll just like really tease it. We're in a shift work study, we've been looking at sort of things that could maybe be like peripheral circadian regulated. And when we do a shift work protocol where we invert the sleep wake cycle, we're seeing the short chain acyl carnitines. You can see this rhythm here. The black is baseline and the red is circadian misalignment. You can see that inverts, that's literally day 2 of a shift work schedule. So these short chain acyl carnitines, whatever's like controlling those in the blood, we're seeing those shift like literally immediately with that shift in probably it's the change in the food intake, not the sleep that's driving it. The longer chain acyl carnitines, I mean, this is decanoyl carnitine. You can see that shift is starting to happen on the red one, but it hasn't happened yet. And there's some other studies that have done similar type of work, but after like 5 to 6 days of the shift work. And so over time, you do start to see that shift happen. But so, whatever it is, these short chain ones seem to be adapting really quickly, whereas the longer chain, maybe medium chain, that's a 10 carbon one, they seem to be adapting a little bit slower. And so that's like really, really, really early work that we're getting going. But there's a lot of interest in like sort of peripheral markers of circadian rhythms. So I'll leave it at that. Kind of my take-home message is that sleep timing impacts light exposure, which impacts circadian timing. So we really have to think about both of these, and perhaps maybe circadian timing is what we can focus on more. From an intervention point of view, it might actually be easier. Like, we're getting people to sleep more, but that's not necessarily such an easy thing to do, to say like sleep more. But changing your lighting environment might actually be a more achievable thing to do. It could be done in the home environment, and as people have more like smart lighting things, and like you can just tell a device in your house or just program it, like you can change the color spectrum of lights really easily. Think like 20 years from now, maybe that'll be what everybody's doing. But so we've, have consistent data showing that morning circadian misalignment due to the short sleep is associated with impaired insulin sensitivity. So I'm asking, what are the best strategies to sort of help people with short sleep duration? And this is kind of the things that I've come up with Tanya, who I mentioned at the beginning. Her and I have started a little bit of work looking at the timing of physical activity, because she has some pilot data in older adults that would suggest that PM exercise might be more beneficial for some outcomes. So we're kind of starting to look at that. There's a lot of interest in it. It's also like there's all of a sudden a couple studies came out, and then like the New York Times is like publishing all over the place, like exercise in the morning to lose weight more, or exercise in the PM. And so like, well, let's do, as good of a randomized controlled trials we can run and see if like this is actually true, or if it's just like all this confounding that like, oh, it turns out people who exercise in the morning do it more consistently and have different diets, and maybe their sleep's better because they can exercise in the morning or the PM or something. So we're kind of starting to look at that a little bit. And, ultimately, I know there's multiple randomized controlled trials going on. There's some starting, looking at kind of these things moving outside of the lab, but overall, there's very few. And so I think like the story is rather incomplete as far as like, what can we do to help improve people's, cardiometabolic risk profiles who are not getting enough sleep, and is telling them to just simply sleep more really the best thing, or do we need to think about other maybe more creative strategies? These are my collaborators and graduate students, and my funding, and I think that's it. Thank you. Yeah, nice to see you. Yeah. Right. That's a really valid point. I shouldn't dismiss it so much. And yeah, so yeah, that's a really good point. And we'll have it. Yeah. Yeah. Right. Yeah. So if that one example turns out to hold true for a lot of our participants, that might actually very well be a major factor. Yeah, that's a really good point. Right. Yeah. Well, 100% we'll have to like look at that correlation and see if they are. Yeah. Right. That is true. We should. It's yeah. Yeah, for sure. That's a perfect description. Yeah. It does yeah, if you just like look at the amount of red, it does look like it. Yeah. Yeah. It's very possible. I we just haven't looked at it yet, so it'll like maybe that'll explain everything, which would actually. It's only one subject, yeah. So yeah, yeah, yeah. But if that's consistent across, if that's what we're seeing, yeah, to all of your points, that would probably explain it. Yeah. And this was just yeah, 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 yeah. It is 20. That's midnight 11. Oh, right, because a clock is only 12 hours. Yeah. But you can't, they do have 24-hour clocks. Yeah, it does. It's, I mean, yeah, active file just spits it straight out, so I can't take credit for it. That's a good question. I haven't this data set's pretty closely balanced between men and women right now, so we can look at that, but I haven't looked at that at all in this one. Yeah. Yeah. Yeah, we'll definitely look at that. Yeah. Right. We tried to control for that. It for sure can, and it can potentially impact insulin sensitivity. We've tried to control for that pretty carefully in the laboratory studies. Um, I mean, we've tracked it here so we can at least like report what cycle they were in. They are hopeful. The hopeful idea by having it by 4 weeks is that hopefully for the insulin sensitivity testing, they're in the same menstrual cycle phase for baseline and post intervention. But yeah, at least for this study. Yeah. Good question. 500 milligrams per day is the level that we use. So that's it depends on where you get your like it's like yeah, 2 to 3, depending on how strong it is. Yes, they do. Yeah, it depends. Yeah, yeah, yeah. It could be a lot. Like, yeah, yeah. Um, I would say that there's no evidence that would support that necessarily. Like the general theory of the central and peripheral circadian rhythms is that mainly like the central clock does help and train central clocks entrained by light exposure like very like almost exclusively. And then the central clock does like all that entrainment. It does help entrain all the peripheral clocks, but things like the timing of food intake and the timing of physical activity can like maybe modulate some of the peripheral clocks. I like I'm not aware of any data that like shows like necessarily feedback from the peripheral clocks to the central clock. And even like I know there's a couple of like studies where they have specifically like even in our study, I didn't show in that like I didn't show the central clock timing, but like we totally inverted sleep and physical activity, but kept them in dim light. The central clock didn't budge at all. So yeah, that's kind of yeah, it's kind of like thought that that kind of yeah. So we're just taking, that's also why I didn't show any like actual calories. We're getting pictures of food intake. And our hopeful idea was that like we could at least capture the timing of food intake. Um, we are having nutritionists analyze those pictures. I don't know. So like 24 hours. 24, yeah. Well, we do it for 3 days. So we have 2 like weekdays and 1 weekend day. Essentially, right. Yeah. Right. Yeah. We're yeah. I'm hoping that we can, oh, I'm not hoping. We're planning on like using it a little more like consistent and like robust methods, which I mean, I don't know. I don't know necessarily know the best. But I'm working with Tanya, like we're trying to like track free living food intake a little more carefully in the RL1 now. So to try and get at that. Yeah. I think it may just be something else that's correlated with insulin. But if we can do, I think, ultimately, if we could do like biopsies and see at the skeletal muscle level if the ceramides are changing there, um, that would be better. I've asked Scott. I don't know how much I know you've met Scott, but I've tried to. People ask him all the time, like measuring ceramides in circulating ceramides in the mice, like what tissue are like what's the primary tissue contributing to that? And I mean, I don't know. His answer is generally like we don't totally know, but he thinks they mainly are coming from the liver. But um, I don't think he's done the studies to like be confident. So just based off this graph, it does look like there's connection. Right. But I wonder if that possibly looks at yellow center. Yeah, you're right. Right. There's, yeah, we need to look at, yeah, I mean, we'll definitely look at like sedentary time. We'll just look at all of it. Yeah. But I mean, you guys are all that. I mean, that is like very perfectly adequate. Like the changes here could be like, yeah, I need to look at more than one person. Yeah. Oh, that's a good question. No, not right. I mean, we do look at that in the lab studies when we restrict people's sleep, and some people are actually become very relaxed in the lab, even though they're not getting enough sleep. Because and like a lot of them have actually seen a decrease in blood pressure living in the lab, just because you're like there's like no stress. You're just chilling. You're doing whatever people tell you to do. You're hanging out. You get food. It's just like kind of a relaxing environment for some people. Like if you don't mind getting clamps done to you and things like that. So, but yeah, we should add that to our own. To yeah. Right. Yes. We've looked at that. It doesn't seem to change dramatically in those lab studies, but also they're kind of being provided, like they're being provided meals, at least in the Colorado studies. We provided them breakfast, lunch, dinner, snacks, and then there was like a set of snacks in the room, but it was all very consistent food. And like all the meals that they were provided were all set to the same macronutrient composition. There wasn't maybe a lot of opportunity for them to start to like change kind of that macronutrient composition. But it didn't. We did look at it, it didn't change. Yeah.
Especially when I think of things like parenthood, things that can disrupt.
Yes.
So I know there's a lot of time between what you're studying here and answering this question. But do you have any ideas about how much sleep deprivation a person can afford? And what really start impacting health and how easily you might correct it, just by getting a forward schedule.
And that's a really, really good question. I can say that in these laboratory studies, if we take perfectly healthy people and restrict them down to 5 hours, I was showing you data over a week, it happens over 2 days, but they also recover really fast. So I don't is that a meaningful, is that meaningful when we're thinking about risk of type 2 diabetes over a lifetime? Probably not. It's,
How much they adapt or adjust to it.
yeah.
Not getting a lot of sleep. Maybe they all are insulin resistant, but
They might. Yeah.
Many of them have short sleep, not just for months, but for years.
For sure. Yeah. We did try to, it's under review right now. We tried to look at in women through 1 year postpartum, we tried to look at sleep duration and excessive postpartum weight retention. And first of all, capturing sleep duration by watches in those women is really challenging because they're so sporadic. So I'm not sure that it's very accurate. But the data that we do, there was no correlation at all with weight retention. So it's a unique time frame, but I don't know. And then Andrea Spaeth, who I know was just here, actually published data where they did find a correlation, I think. And our study was very similar to theirs. So